Okay, good day everyone. We shall begin this presentation in the ancient lands of Sumer. Why Sumer out of all the places? That boils down to the number system the Sumerians came up with. As we shall see shortly, this number system would have a significant influence on many of the number systems that were to follow over the ages. Thus, without any further ado, let's dive in. From historical evidence uncovered so far, the Sumerians seem to have used a number system based on the number 60. They would have thus used the phalanxes on the fingers to count from 1 up to 12. Thus the topmost phalanx of the index finger would represent number 1, the second phalanx, number 2, and the third, number 3. Thus using the 12 phalanxes, they would have been able to count up to number 12. Now let's fast forward to number 10. And once they have counted up to number 12, they have come up with an ingenious solution of transferring this count onto one of the fingers of the left hand. As we shall see later, this transferring of a count from one set to another set will play a crucial role in most all modern counting systems. And now the thumb of the left hand is used to hold a count of 12, thus releasing or freeing the right hand to continue the counting from 12 onwards. And now if one want to know the total count at this point, one would have to add up the 12 we transferred to the left hand to the count we have in the right hand, thus giving the total as 15. Though at first sight this method or technique may seem very trivial, it is nevertheless a forerunner or even forms a basis for what we nowadays call the base number systems. We shall look into the modern base number systems towards the end of this presentation. Next, let's fast forward to where the right hand has counted up to number 11. And now again the right hand has again counted up to 12, which is the physical limit or the maximum one can count using the phalanxes. Thus yet again, we shall transfer this count of 12 to a finger of the left hand. And now the left hand holds 2 sets of 12s, which brings the total to 24. For the moment, make sure to keep a good visual impression of this technique of transferring numbers from the right hand to the left, as this technique will play a crucial role in the base number systems we shall look into later. Thus observe that using this technique of transferring counts from the right hand to the left, the Sumerians would have been able to represent 5 sets of 12s in the left hand, thus bringing the grand total to 60. And this is how this counting system, which is based on the numbers 12 and 60, would have had originated. If anyone had have wondered as to why there are 12 digits on the face of a clock, or as to why there are 60 seconds to a minute, or 60 minutes to an hour, or as to why there are 12 months to a year, or as why ancient astronomers divided the sky into 12 sections or 12 zodiacs, now you know the origins of all of these numbers, and how they would have had originated and evolved over possibly hundreds or thousands of years. Also observe that by transferring a count from the right hand to the left, that we have freed or emptied the right hand. Thus reflect how this is yet again a forerunner of the notion of the number 0, which mathematicians would formally develop only a few thousand years later.
Next, let's ponder a bit at the theoretical or fundamental question as to whether mathematics would have originally been discovered or being invented. Without directly answering this question, let's go back into ancient Sumeria, and let's take a case of a construction materials supplier. One sunny summer morning, a few officials from the royal court of Kish pays him a visit and inquires on how many large-sized bricks he has in stock. Apparently, the royal court has sanctioned the construction of a new ziggurat, and now the courtiers are scouting the countryside, collecting and auditing the available construction materials. Now our good friend the construction materials supplier, without a moment's hesitation, responds,
"Certainly, give me 5 minutes."
And goes to his storage compound and starts counting bricks. To add further drama to our story, it's 1 o'clock past noon, on a clear summer day, and the temperature is 40 degrees Celsius in the shade. So 5 minutes turns into 10, 10 minutes into 20, 20 minutes into 40, and all this while, the guys from the royal court are waiting. And waiting. and waiting, and losing their patience. Now, on the other hand, if our good friend knew the techniques of multiplication, wouldn't his life had been much more easier? If that would have been the case, most likely 5 minutes would have been more than enough. Thus, to bring back the question as to whether mathematics would have had been discovered or being invented, it is our view that prior to the advent of career mathematicians or those engaging in recreational or inquisitive mathematics, the first usage of mathematics would have evolved or originated out of pure necessity. Thus, for example, a farmer would need to count the number of sacks of grain, or a shepherd would need to count his livestock, and then merchants would need to count the items currently in stock. Thus, it is our opinion that in most likelihood, the roots of mathematics would have been laid in pure day-to-day necessities. The English language proverb, "Necessity is the mother of inventions," comes to mind. Now, in the case of counting bricks, a knowledge of mathematical multiplications could resolve that problem. But how about if one wanted to count the number of cubits in a pile of sand? Now the mathematics involved are going to get more complicated. Thus, we observe career mathematicians over the ages studying and analyzing on the such of how to calculate the areas and volumes of objects. Thus observe that in most likelihood, in the case of mathematics, it was first invented or devised by people to resolve day-to-day issues, and then later on individuals the such of mathematicians would have had started pondering and perusing these problems further, thus discovering some very intricate and elaborate techniques, relationships, and phenomenons. The such of Pythagorean theorem, the value of pi, and solutions to quadratic equations comes to mind. Current archaeological evidence points that even around 2nd millennium BC, mathematicians knew how to solve the such of quadratic equations. For example, the clay tablet showcased here describes a technique to find the square root of the number 2. Next, we shall take a look at the decimal number system widely in use in the modern world.
In this section, we shall mostly let the viewer observe, visualize, and discern how the decimal counting system is utilized. In the next section, we shall resume the audio presentation. Thus, in this section, just observe and make a visual comprehension as to what's going on. And in this closing section of this presentation, we shall take a summary of what we covered, with an emphasis on the fundamentals of base number systems. If one could recall, in the Sumerian number system, each time we counted up to 12, we transferred that amount to a finger of the left hand. Like so, in the decimal counting system, each time we count up to 10, we transfer that sum to the tens count section. Thus 15 represents one set of tens plus 5 ones, and 32 represents 3 sets of 10s plus 2 ones. Thus, if we take the decimal number 523, what it represents is 5 sets of hundreds plus 2 sets of 10s plus 3 ones. But we also know that 100 can be represented as 10 multiplied by 10 or 10 to the power of 2. And 10 can be represented as 10 into the power of 1. And 1 can be represented as 10 to the power of 0. Thus, for the moment, keep a mental image of this pattern, and it would become clearer when we analyze the next number. Now we shall analyze the decimal number 9523. And as a technique of understanding this core fundamental of base counting systems, it will be left to the viewer to observe this dissected number and identify the core patterns. Thus, observe that in the base 10 counting system, better known as the decimal counting system, how we count in sets, which are powers of tens. Thus, at the rightmost end, we have the tens to the power 0, which represents the ones. Next, we have the tens to the power of 1, which represents the tens, followed by the tens to the power of 2, which represents the hundreds. Next, we have the tens to the power of 3, which represents the thousands. Now observe that just as in the decimal counting system, where we use sets of tens or sets of base 10 to do the counting, it should also be possible to use a set of any size for counting purposes. For example, recall that the Sumerians used a set of 12. Thus, in the next set, observe we have used the base as number 8. Thus, in this base 8 system, better known as the octal system, we have used sets of 8s to do our counting. Now observe that 7, 5, 2, 3 in the octal or base 8 system actually represents or is equivalent to the number 3923 of the decimal system. And next we shall look at the base 2 or the binary number system, which is at the core of all functionalities inside computers. The binary number system is most useful in digital computing, as it represents a circuit that is off via the number 0 and a circuit that is on via the number 1. Also, just as any other number system, the binary numbers can also be used to represent numbers. Thus, observe that in this demonstration, the binary number 0, 1, 0, 1 actually represents the decimal number of 5.
And that brings us to the end of this presentation on number systems. As we had to cover all the way from 3000 BC, this video ended up a bit longer. Of course, there is much more to cover, but we shall leave all such for future videos. And as always, if you did enjoy this video or found its content useful, do give us a like, and also don't forget to subscribe. Okay then, have a nice day, and see you in our next video. Bye.